Yeah, hello. My name is Thomas Kroll. I'm a scientist at SSRL, and I'm gonna give you a little introduction to X-ray spectroscopy at SSRL, uh, with some examples of beamlines and what information you can gain. So generally speaking, in X-ray spectroscopy, an incoming photon excites an ion to an excited state, and successive decay leads to the emission of an electron or photon that then can be detected. And generally speaking, there are three methods: X-ray photoemission spectroscopy, or XPS, X-ray emission spectroscopy, XES, and X-ray absorption spectroscopy, which is XAS. And the latter two can be combined, giving RIX, or resonant X-ray emission spectroscopy, which is resonant XES. For the photoemission, there's also a special case, which is angle resolved photoemission spectroscopy, ARPAS, which is also very prominent at SSRL. So let's have a look at some of the method. Let's start with photoemission spectroscopy. Let's say we have an iron ion. All shells are occupied. The 3D is only partially occupied. And we come in with an incoming photon, which excites, for example, the p electron into the vacuum. And that electron can be detected. And what we detect there is its kinetic energy. And the kinetic energy gives us information about the binding energy, simply by subtracting the incoming photon energy minus the binding energy. That is the kinetic energy. And so, or the other way around, the binding energy is h nu minus E kinetic. And so by running through the kinetic energy, we can get a spectrum that looks, for example, like this one here for iron. Here we have the iron 2p 3/2, iron 2p 1/2 region, 3/2 and 1/2 because we have a hole in the 2p. We have LS spin-orbit coupling, meaning J equals 3/2 or 1/2 because L equals 1, S equals 1/2, and then it's 3/2 and 1/2. And since it's a strong spin-orbit coupling, we usually speak about JJ coupling. And so, besides the two regions, you also have a lot of final states underneath. That's because the 2p electrons, they interact with the 3D electrons, meaning that from these curves you get information about the 3D orbitals, including like ligand mixing, which gives rise to the satellite, a little bit of geometry, and the number of electrons. There's a little specialization here also for photoemission when you do it at the valence bands, and also you can vary the incoming energy and the momentum transfer, which then means that you get angle resolved photoemission spectroscopy, which can give you direct information about the band structure of solids. Unfortunately, I cannot say anything about it in this presentation due to time constraints, but I highly recommend that you look into these because there's a lot going on in this field. Another method is X-ray emission spectroscopy. So initially we have the same thing. We have an incoming photon exciting an electron, this time it's 1s, into the vacuum. And what happened then is that, well, we have a 1s hole, and that hole, once it gets filled, and it gets filled most likely by a 2p electron, which then emits a photon. Or it emits an Auger electron, which both can be measured. In this case, we detect a photon, and when you scan through the emission energies of that photon, you get the full spectrum. This one is a K alpha because it's from a 2p into the 1s. We have a 2p core hole left at the end, meaning again we have a J equals 3/2 and J equals 1/2. And also here there are a bunch of various final states underneath, even though the two peaks look relatively symmetric. So now if you don't excite the electron from the 1s into the vacuum, but you excite it into an unoccupied orbital, which in this case would be a 3D orbital, for example, you do a resonant excitation, which is then X-ray absorption measurement. So the photon gets absorbed, and if you measure in transmission, you basically do count the intensity that comes in, and you count the intensity that comes out, and you can couple them through I1 equals I0 times e to the power of minus mu times x. X is the thickness of your sample, and mu is the energy-dependent absorption factor, or absorption coefficient, which describes your sample. But you can also wait for the decay, like here, and then detect the emitted photon. And when you do that, then the intensity is just the emitted photons divided by I0, which then gives you the information about the absorption coefficient. And when you combine these two, you get resonant emission spectroscopy or resonant inelastic X-ray scattering. These are two names that describe the same thing. It's a little unclear what is what really, so it doesn't make sense if you say, in this case, for example, you would do 1s 2p rigs. Then everything's clear what you talk about. And what is quite nice about X-ray spectroscopy, at least when core levels are involved, is that each core level requires a different X-ray energy, which is given by the excited ion, meaning that X-ray spectroscopy is element specific. And you see that here very clearly, again, in the case of iron, the 1s binding energy is around 7,130 eV, the 2p binding energy is around 730, and the 3p is like 56. So these are vastly different, like a factor of 10 between 1s and 2p. And they're different not just for iron itself, but they're also different for cobalt, for manganese. There are no two that are exactly the same. Another thing is that, as you see, the energies are very different. They fall into different regimes. And generally, we just put them into the soft X-ray, the tender, and the hard X-ray regime, with the difference between them being the X-ray range. So soft X-ray is usually like 100 to 2000 eV, the tender like 2000 to 5000, hard X-ray is like larger than 5000 eV. And the consequence that has is that the penetration depth of the photons and also the escape depth of the electrons varies. It gets larger the higher the photon energy is, which then has consequences on what kind of sample environment you need to employ. For soft X, for example, you usually require UHV, an ultra high vacuum. Sometimes you're good enough with a high vacuum, but you cannot do it in air because the photons will get absorbed very quickly. Tender is even better, and hard X-rays, you can do experiments in air, in a gas, in a solution. You have a lot of more flexibility. And at SSRL, we have a large number of beamlines that can do spectroscopy in all the three regimes. And here I will talk only about three of them: beamline 9.3, beamline 10.1, and beamline 15. 10.1 is soft X-ray, 9 and 15 they're both hard X-rays. If you want to know more, I highly recommend you go to this link and have a look at all the different beamlines that are available at SSRL. So let's start with beamline 10.1. It's a soft X-ray beamline. It can do X-ray absorption and it can do rigs. Here's a picture of it. The photons that come in here from the right, around where the blue line is. This here is a chamber. Of course, everything is like inside the chamber. Sample is around here, and next to the transition edge center, like a TAS detector, in order to detect the photons. But there's also like sample current that you can measure. There's a channeltron for the partial electron yield and silicon diode for the total fluorescence yield. So everything is within that chamber. In order to get your sample in there, here's anti-chamber, anti-manipulator, so that you can bring your sample from the outside into the measurement position. And that beamline, it has an energy range of like 250 to 1200 eV, so you reach the carbon K edge easily, and it goes to zinc and a little higher. Spot size around 1 by 1 millimeter squared, with a flux of up to 10 to 12 photons per second. And in sample environment, as I said, it must be UHV or at least a high vacuum, which means that the sample you measure are typically solid samples, which do not outgas a lot. But you can also put in frozen solution samples, or you can even measure solutions if they're behind a silicon nitride window. And so what you measure with this? I mentioned already the carbon K edge. Here I want to focus on an iron L edge. And an iron L edge we excite from a 2p into an unoccupied 3D orbital, which means we probe the valence orbitals, the unoccupied valence orbitals, which means that the spectrum is then very sensitive to the electronic structure, like which orbitals are occupied or partially occupied, what is the spin and the oxidation state, what is the local geometry, covalent mixing, etc. And here on the left, I give now 3 examples in gray, yellow, and black. gray, it's a little difficult to see here. That's an iron 2 low spin complex, S equals 0. Yellow is an iron 2 intermediate spin, S equals 1. And black is an iron 3 low spin, S equals 1/2. And just by looking at them, they look vastly different. So you have a good idea already if you measure a complex like the one here in pink, which is an iron pictofence porphyrin with an O2 axial ligand, and you compare them to your reference spectra, and then from that you can already say, okay, that looks pretty much like an iron 2 low spin. It's not exactly the same, so there are small differences, but roughly speaking, that's your first idea. You can do some more detailed analysis using, for example, some codes like multiplex calculation that includes charge transfer, using the VBCI model, which is the valence bond configuration interaction model, or actually these days there are also quite sophisticated methods using ab initio calculations. They can calculate LHs relatively good. And so in this study here, what they found, first of all, the quality more similar to an iron 2 low spin, S equals 0, but a more detailed analysis and actually gave the more insight or in-depth information that there's a strong sigma donation from the O2 into the Z-squared orbital of the iron present, as well as a strong pi interaction with the porphyrin and the iron. And this had all been measured using the partial electron yield. You can also measure, of course, a fluorescence yield, and now let me come to the transition edge sensor, the TES detector, which is a medium resolution fluorescence detector for highest throughput emission detection. And what it does, actually, it uses a superconducting material that is cooled down around the critical temperature. And now when a photon, like an emitted photon, hits that sensor, it heats it up because it dumps its photon energy into the sensor, meaning it heats it up. It changes the resistivity because it's a superconducting one where you're at the close to the critical temperature. And so then you have a resistivity, which is something you can measure, for example, or you measure the voltage that goes with it. And so you have quite a resolution that you reach with that one. It's around an EV, 1.5 EV, getting better with every new version. And the big advantage is, even though it's not high resolution measurement, but you record the full emission spectrum at once. You record the emission from all various lines. For example, here you have the 3D to 2p, you have 3s to 2p, you have the oxygen emission, the nitrogen, the carbon, everything comes in there all together, meaning there's no need anymore to select a specific region prior to the experiment, which is a very good thing. It also gives you, for example, the oxygen, the inverse partial fluorescence yield. Like you scan over the iron LH, and you get the inverse, which is shown here, which is proportional to the actual absorption of the iron, but without any self-absorption and saturation effects. And what we show here, since you always get a Rix plane, independent of what you do, it always comes for free. Here we compare 500 to 5 millimolar, and here's the Rix plane. And if you integrate the Rix plane, you get the partial fluorescence yield. But also, since you have the Rix plane, I mean, you see a lot more detailed in the 2D than in the 1D curve. You can do vertical cuts, which then give you additional information about it. And what is shown here, while we show 500 millimolar and 5 millimolar, it actually shows that you can measure a low concentration sample as a frozen solution, which is a quite powerful method. All right, let's leave the soft X and let's go to the hard X rays. It's beamline 93. It's beamline to measure X-ray absorption and EXAFs. It has a simpler setup because now everything can be in air partially. So the beam comes here from the right, in blue again, goes through an ion chamber for I0, and then it hits a sample, which is around here. Sample does its trick and it radiates into hole 4 pi. In particular, it will radiate here into 100 element germanium detector, where you then count how many photons you got at a given incident energy. And if the photon actually is transparent enough to photons, some of them will go through, and then can collect them here at I1 at another ion chamber. Now actually note that I took that picture here when it was not in operation, so don't worry that there is no actual sample, and also ignore that there's actually a cap on the detector, so that the detector wouldn't measure anything in that specific setup, but the principle is pretty clear. Here, by the way, that's a cryostat that is not mounted. You can bring it here right into the position for the sample and measure down at like 10 Kelvin. So then this beamline, as I said, is a hard X-ray beamline. It has an energy range from like 5 to 30 keV. Spot size like 1 by 4 millimeters squared that you can slit down if you need less photons. Or if you need more spot sizes on your sample, with a flux of around 2 times 10 to the 12 photons per second. And as I said, since these are hard X-rays, the sample environment is a lot more relaxed. Like everything can be done room temperature if you want to. Ambient pressures are okay. You can use a liquid helium cryostat, measuring frozen solution camp samples like 10 Kelvin. You can use electrochemical cells, or you can use like a beryllium reactor for like high pressure studies. So you have a lot more options to design your experiment, and you have a lot more access, just because there's no vacuum that you have to fight with. So the RNK edge now is a little different than the RNL edge, in the sense that now we have quadrupole and dipole transitions. So a quadrupole transition would be an excitation from 1s into 3D, and a dipole from a 1s into 4p, which then has the consequence that you get multiple regions. So here's the pre-edge region. There's an excitation from 1s into 3D, which means it's quadrupole, and that's why it's so low in intensity. However, you can gain some 4p mixing if you lose the inversion center, and then 4p can mix into 3D, which is dipole, and then you can enhance intensity. You have the edge region, or the XANS region, which is sensitive to structure information, and then out here, you have the extended X-ray absorptive fine structure region, or XAFS, which gives you purely structural information. I want to illustrate that here in a little example. This is a study done on iron-4 model complexes. Shown here, it's our iron-4 oxo bonds with different axial ligands underneath it. So this one is a 5 coordinate, these other 3 are 6 coord with different axial ligands. And when you look at the pre-edge region here, you see that the intensity increases. And the intensity increases because we have no inversion center. We have a certain amount of 4p mixing into 3D orbitals, which increases the intensity. So the pre-edge intensity is determined by the coordination and also by sorting of the bond lengths. If you do have an inversion center, then you don't have any 4p mixing into it, because gerade and ungerade in group theory they can't mix. And so then the pre-edge region is weaker in intensity, maybe let's say a factor of 2 or so weaker easily, but it does give you more information about the unoccupied 3D orbitals. So now when you then go and measure the XAFs, you get it in K-space, you do Fourier transform, you get it in the direct space, and then you can look at your data. And what we got out from here, or what they got out from here, I was not involved in that study, is first of all, they all have short iron oxo bond lengths in all complexes. That's pretty expected. But actually there is a different bond lengths due to the different axial ligands, because these axial ligands, they tune the bond lengths. And since they do that, they impact reactivity. A similar beamline like 9.3, but with a special twist, is beamline 15.2. It's a relatively new beamline. It's an undulator beamline, and it's for advanced spectroscopy, or it's called advanced spectroscopy beamline, and can measure XAS, XES, and resonance X-ray emission. And the principle is the same thing. You have the photons that come in, here again in blue, and here you have a beam conditioning unit. Here's the sample. The sample does the same as what they would do at 9.3. For example, they emit K alpha radiation, and they do that into the whole 4 pi angle. But now, instead of collecting that with one big detector, we have this 7-element Roland detector on a meter away with analyzed crystals. And so when K alpha emitted, or any emission lines emitted, Some of it will make it to the analyzer crystal, and a certain energy will be selected, which is given by the crystals and the angle. And then it's focused back into the detector and is measured. And the existence of this additional spectrometer, that makes it advanced. There's also 40-element spectrometer that we use for Raman scattering. We don't really, I will not go over that in this presentation, but it's a very nice method and you should read about it if you have time. The beamline also has a laser system, so one can do pump probe experiments on down to like less than 100 picosecond time resolution, and we have KBs so that we can tune the size of the incoming beam. Energy range is very similar to 9.3. What's very different is we can tune our beam size. We can go down to like 5 by 35 microns. We can open up to like 100 by 800 micron square with the KBs. And if we take the KBs out, we get a beam size of around 0.5 times 2 millimeters squared. With a flux of like 4 times 10 to the 13 photons per second at the RNK edge using the silicon 111. We can also use the silicon 311 that gives you a better resolution and around a factor of 7 less photons. Sample environment is pretty much the same, since all hard X-rays. Since we can bring down the spot size so much, we can also do high pressure cells, like using diamond anvil cells, and you can use liquid jets. Alright, so the emission. Let's talk about that a little more. So we excite a 1s into the vacuum. You're left with 1s hole, which gets filled either by a 2p electron, a 3p, or a valence electron, which means you have different emission lines, namely the K-alpha, the K-beta, and the K-beta 2.5, or valence to core. And what is pretty clear in these ones here is A, they all look different, meaning they have characteristic line shapes, which can be interpreted, and they also are very different in intensity. The K-alpha is the most probable one, so it's highest in intensity. The K-beta is around a factor of 8 less than the K-alpha 1. And the valence to core, which is like this teeny tiny signal here, is around a factor of like 50 to 100 less than the K-beta, which means it's around a factor of 1000 less than the K-alpha. However, it can still be measured. You see it here pretty nicely, and it does give a lot of information. I will go over it in the next slides. So let's start with K-alpha. While the K-alpha emission also has good information, what is very often used is for HERFT, high energy resolution fluorescence detection. So when you think back to a time at 9.3, a couple of slides before, and do an emission or you do an experiment and you detect the K-alpha signal with a detector, which is a germanium detector, it has an energy resolution of around 200 eV, you would get a spectrum somewhat similar to this, let's say. Here you have the elastic peak, you have Compton scattering, and here you have the inelastic intensity from the K-alpha emission. And since the resolution is so bad, you cannot separate anything. So what you do is you set a window around here, what's given in blue, in light blue, and you just integrate whatever's in that window, and that is your intensity for a given absorption energy. And then you build your spectrum, which would look somewhat like this here, similar to what I have in blue. With an emission spectrometer, you can actually resolve the K-alpha, and it looks like this. And then you set your emission energy to one given energy, and you only select out that one, which means you dramatically increase the resolution of the spectrometer, or of your data, and instead of the blue, you now get the red curve. And even that is not even a good data. It's pretty noisy, because I did not spend any time on it. You clearly see huge differences. I mean, this peak before it was small shoulder, now it's a real peak. And also here in the shape resonance, you see a double peak structure instead of something broad. If you want to see better spectra, here are 2 examples where it has been done, but there are many other papers out too. Another big advantage is that there's basically no background, because we reject everything that does not fall into the small energy window. And you see that here. It's practically background free, while the other one has quite a background underneath, which means you very quickly get out all the features you need. And that means you can go down to very low concentrations. For like biological samples, you can go to traces in like environmental sciences, or you can do operando catalysis, where you have to go through a number of different components before you reach the sample. And so here's an example where HERFT had been used. That's for like a platinum etch electrochemistry experiment. Here again, at platinum, it's even stronger. Like platinum's at higher energies, the core lifetime is broader. The difference between the total fluorescence and HERFT, it's like night and day. And so when you look at the data given at different at voltages, you do now observe with HERFT small changes in the energy, small changes in the intensity, which will be completely invisible when you did normal XAS. We don't have just K alpha. We also, as I said, we have different emission lines. So let's look at K beta. K beta is the decay from the 3p into the 1s. So you're left with a 3p hole. And let's look at the example of manganese chloride. Manganese chloride is a D5 high spin. So all 5 electrons or 5 spins are parallel in the T2G and the EG orbitals. And so the 3p has a weak spin-orbit coupling. So we stay in the LS coupling regime, which means spin is a good quantum number. And then the split, or the whole spectrum is given by basically the 3p 3D exchange interaction. And so the main peak here, the KB13, we have a configuration like this, where this 3p electron that's left is parallel with the 3D electrons. Now, when you flip the 3p spin, as it's here, the energy changes. Think about Hund's rules. It's at a higher energy, meaning it's a lower emission energy. And they're split by like 12 eV or 13 eV. It's quite a bit. And you have some more structure in here, which is due to different 3D configurations. So now let's think about a different case. What about the T2Gs are all occupied, like in D6 low spin, and EGs are empty. So if the spin equals 0, then it doesn't matter if the 3D spin equals 0. It doesn't matter if this 3p electron is spin up or spin down, because that would be degenerate. So the KB must overlay with the KB prime must overlay with KB13, and you would expect only one peak. And that actually is pretty much what you observe. So here in that figure, there are a number of different spins are shown with the corresponding spectra. The high spin, now here only have a quintet, so S equals 2. We see the KB primes, and you see the main line split quite a bit, and in the singlet, you don't see that splitting anymore. You still see some intensity here, and you see like an asymmetric line shape, which is not due to the presence of a KB primed, but that's due to the same as what I said before. You also have different configurations of the 3D electrons, which actually then give rise to different energies in different transitions. So it's a very nice method to actually measure the spin and learn about the spin. And if you want to do it more quantitatively, there are also methods like the integrated absolute difference, the AID method, or you look at the first moment of the KB13, or look at different spectra as is usually used for time-resolved measurements. If you go around like 6 dB higher in energy for iron, then you had the valence bands. And if you now look at the decay from the valence to the 1s, you get a weak signal. As I said, it's around 1,000 times less than K alpha 1, but measurable, and has a lot of very nice and very good information. The interesting thing is the valence to core region is mostly sensitive to the ligand characterized excited ion. And here is the example of 3 different complexes, TACAN, ACAC, and hexacyanide. They're very different ligand environments. They also have different spin states, and the spectra are vastly different. So a lot of information lies in these, and you can also simulate them just doing like ground state DFT calculations, and you can get a spectra that actually reproduce the experimental spectra reasonably well. And it's a pretty powerful method. So finally, as kind of last example in the presentation here, we talk about RIGS, which is gives a little twist to the absorption that you have mentioned before. Let's again use iron. We excite from the 1s into the 3D, which means we do a KH absorption, and we end up at an immediate state like this. It's a configuration similar to this one. And now the one S hole will be filled with the 2p, leaving a final state configuration. It looks like this here. And what's interesting is that this final state configuration, you can also get it directly by just exciting from a 2p into the 3D, which is an LH experiment. It's a soft X-ray experiment. The other two, they're all hard X-rays, and this one is the same final states as in soft experiment. And that's particularly interesting because the soft X-ray, it has a lot of features, a lot of peaks, and you can interpret the data. When you do the experiment as a K-edge for the same complexes, it is pretty broad and not so information rich. But since we now reach the same final states, we do get something that's similar to an LH. And so when you measure these, you get these the two-dimensional planes. Incident energy on the x-axis, energy transfer on the y-axis, which is LH-like. And you get two-dimensional planes that are highly, have a lot more information and than just a 1D plane. And you can basically do two things. You can integrate it, and you get a K-edge. You can do a diagonal cut, which is shown here. The CE cut, which are the constant emission energy, which means it's exactly the same as HERFT, what I explained a couple of slides before. You can also do vertical cuts here in green and in red, which are then LH-like cuts. They give an LH-like information. It's not exactly like an LH because we have different selection rules, but it's LH-like. And you can actually compare these two and learn from it. So in this study there, we did a quantitative analysis using charge transfer multiplier calculations that we then coupled DFT calculations. And then, upon going from the model to the protein, here on the left, that's TPP bismuthazole. On the right is oxidized cytochrome C. The main difference is the model, it has one of the actually the histidine, and the MET is the other, or it's a corresponding ligand for oxidized cytochrome C. And when you go from his to MET, then you find decreased Z-squared metal character, you find a decreased pi metal character. You also find that the iron 3 has a higher covalency than the iron 2. And when you take this all into account, couple the DFT calculations, you find that there's quite some implication on the iron sulfur, which is from thionein ligand, that it affects the bond strengths. And you can get quite information about the bond strengths and also then the enteric state. With that, I'm at the end of my presentation. I want to say that I want to show you that a number of people at SSRL work in the range, in the area of X-ray spectroscopy, in the soft X-ray, in the hard X-ray. Very good people. They're all very nice. They know very, very well about their methods, and you're more than welcome to write an email to anyone if you want to do an experiment and ask them about it or ask them general questions. And with that, I thank you very much, and I hope that you enjoyed this little introduction. Thank you.